So this is the 2-bit analog to digital converter circuit. So what we have here is we have 3 op amps, and these op amps are working in what's called comparator mode. So when you have a signal coming in, so this would be the signal coming in from your analog sensor, and if that signal gets above a value if set by these resistors, then it triggers the comparator on. So let's look at the first case. So if the signal we have over here, we have a voltage divider circuit, and the 2-bit analog to digital converter, that means you have 2 to the power of 2, which gives you 4 possibilities. But those 4 possibilities are 0, 0, 0, 1, 1, 0, and 1, 1. That's the binary case. Those are the 4 possibilities. So, the first possibility is that the voltage is so small that you don't recognize it. And so if the voltage is here fluctuating around, but it doesn't pass this threshold, then you're going to be outputting a 0, 0. So this is a 0, and this is a 0, and this is a 0. Now these are called inverters. And so if you put a 0 into an inverter, you get a 1 out. If you were to put a 1 into the inverter, you would get a 0 out. So these are little inverter circuits. This is called a NOR gate. And so the way a NOR gate works is if this is a 1 and this is a 1, okay, then you get the opposite. Let's look at the truth table here for the NOR gate. Okay, so the first thing we have is an OR gate. So the OR gate, okay, the way the OR gate works is if you have, you have your 2 inputs here. So if you have a 0, if they're both zeros, then you get a 0. If you have a 0 and a 1, that's either or, you get a 1. So this is the OR condition. Let me swipe this over. Now, and then this little bubble is the inverter piece. Okay, so this is not OR. And so if it's a 0, it's a 1. If it's a 1, it's a 0. So with the OR, if you have a 1 and a 0, it's either or, so it's still a 1. But a 1 and negated through this inverter, this bubble here, makes that a 0. And if it's a 1 and a 1, well then at least one of them is a 1, and so that gives us a 0. So this is a NOR gate, and the NOR gate is a 1 only when both of these are 0. Okay. So as we look here in our cases, we have a 0 here and a 0 and a 0, because the voltage is below this voltage threshold here of 1.67 volts. All right, so we have a 0 and a 0 and a 0. So if we look at the case of the NOR gate, right, we're putting in a 0 here, and we're putting in a 0 here. Now this is called an AND gate. The way the AND gate works is you must have a 1 on both sides to get a 1 out. So if 1 and, the first input is a 1 and the second input is a 1, then you will get a 1 out. Otherwise you get a 0 out. So if we put a 0 out here, this is going to be a 0. So we have a 0 and a 0, which makes this a 1. That's the only case where the NOR gate is a 1. However, we're going to invert that again. So that's a 1 there, a 1 there. We get a 0. And so this is a 0. And then this one here it's 0, it becomes a 1, and then 1's going in, so we get a 0 out, so that means it's not lit. So that's the first case when we haven't broken the threshold. Now the next case is when the signal does actually come up above this threshold. So the signal is somewhere above this threshold here. All right, but it hasn't broken the next threshold. And so we're up above here, so that turns this one on. So this becomes a 1. So this is a 1 here. And this is still a 0 because we haven't broken this threshold, so that's still a 0. So we have a 0 going through the inverter becomes a 1. So we get a 1 here and a 1 here, and this is the AND, right? So if I have a 1 and a 1, 1 and 1, that gives me a 1 out. All right. So a 1 going into the NOR gate. A 1 going into the NOR gate, that's this table over here. Anytime I have a 1 in there, the NOR is giving me a 0. So that's a 0, which makes this one a 1. Okay, so that turns on this. So that's a 1 condition there. All right, so if my voltage is above 1.67 volts, then I have a 1. So we have all right, so we have the case where the voltage is below So we have the case where the voltage is below 1.67 volts. So if the voltage is below 1.67 volts, we get 0, 0 out, right? Which is decimal 0. If the voltage is between 1.67 but less than 5, we're going to have a 0, 1 out. And if the voltage is 5 or better, but less than 8.33, we would have 1, 0 out. And if the voltage was 8.33 all the way up to 10 volts, I would have a 1, 1 out. So that would be, oops, sorry, that was a 1, this is a 2, and this is a case 3. All right, so the way this works is you're going to have the highest value you could possibly have, which is 1, 1 in binary, or the value 3, anytime the voltage gives above 8.33 volts. All right, so let's take a look at a 3-bit converter. So we're going to go up 1 bit. And so if we looked at the circuit here with the voltage divider, so if we look at the case where it's a voltage divider, let me get the 2-bit back up here one more time. All right, so looking at this voltage divider piece here, all right, you see that we have a 2-bit converter, which means the maximum value you can have is 3. So you take 10 divided by 3, and that gives us 3.3 volts per bit. All right, but you see here that we actually have 4 resistors. 2 of the resistors are 2K, but then the other 2 resistors are like the third resistor split in half. So you got half above and half below. All right, and so that gives us this threshold difference here. So the each step from here to here is 3.3 volts, and from here to here is 3.3 volts. That's the resolution, or the volts per step, or the volts per bit. So, or per count, actually, is probably a better way of saying it than per bit. So every time we advance the count, it means we moved up 3.3 volts. However, by splitting this third resistor and putting half on top and half on the other, what that means is that we're going to get a little more sensitivity. See, if we didn't do that, if we just had 3 resistors of 2K to break up the 3 non-zero possibilities, then we would have to have exactly 10 volts to trip this highest value, which is seldom, if ever, going to actually happen, right? You could have 9.999 volts and you're still not at 10. So remember that these analog to digital converters, you have to cross the threshold. They do not round up. You have to be at or above the threshold for it to actually trigger. So if we go up and look at a 3-bit converter then, all right, so here is a 3-bit converter. And so with the 3-bit converter, you have 2 to the third possibilities, right? Which means that you have 8 possibilities. So those 8 possibilities, remember the first possibility is all zeros. Okay, so you have 0, 0, 0, and then 0, 1, 0, 1, 0, 1, 0. Right, it's 3 bits, so you got to count all 3 bits. So 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and of course all ones, which is 7. All right, so if we went to calculate the resolution, okay, so our resolution then is going to be, and this is a 0 to 10 volt converter here. So it's looking for a voltage somewhere between the lower limit of 0 and a higher limit of 10. And so if so we take 10 divided by the maximum value, right, minus the low value of 0 volts divided by the low value of 0. Okay, so you end up with 10 divided by 7, which gives us a resolution of 1.43 volts to 3 digits divided per count. Right, so like I say, bit isn't a good word, it's really per count. So every time you go up 1 count, 1, 2, 3, then you're going to be going up. You're going to be going up by the resolution, okay, by this resolution of 1.43 volts. But if we built this circuit, okay, with 7 resistors, okay, so if we built this circuit with the 7 resistors, here's my 7 resistors, 1, 2, 3, 4, 5, 6, 7. So if we built that with 7 resistors, right, then the very first value we would be able to detect would be that resolution of 1.43 volts. And then the second voltage we would be able to detect would be twice that. All right, and all the way up so that the 7th value would be 10 volts. But again, 10 volts is the maximum limit. So even if we're just slightly below the 10 volts, we're not going to detect that. And so the way they build these is what we call the symmetric analog to digital converter. So again, what we're going to do is we're going to take this top resistor here, basically split it in half and put 1K up here at the top and 1K down here at the bottom. So instead of the first voltage that we would be able to detect being 1.43 volts, we're going to detect half of that at 0.71 volts. So the distance between each one of these is going to be 1.43 volts. Except for this first line, because the first line is going to be 0.71 volts. Okay. And actually the last line, which is going to be, right, for this distance right here, would be 0.71 volts. All right. But what that means is that the maximum voltage that we can detect is going to be 9.29 volts. Okay. So if our voltage gets up here and crosses this threshold of 9.29 volts, my output of my converter is going to be 111, which is 0.7, and so that's going to be the value that I'm going to be reading in. So I have to, but I remember I have to cross this threshold to get to that value. All right, so again, the reason we do this is because if we just did like all the same resistors in this voltage divider, then your maximum value of 111 would only be able to detect the absolute max of 10 volts, which is really going to be a very rare occasion that probably even comes through, especially when you think about the attenuation. By the time it gets to our thing, even if it drops just a fraction of a volt, it's not 10 volts, it's not going to be triggered. So we do this symmetric circuit where we put just a fraction, where we use even number resistors. Now in this example I'm using 2 kilo ohm resistors, which are probably kind of small for most cases, but it doesn't matter what value the resistors are, it matters the ratio of the resistors. So as long as they're all the same, then you're going to have an even separation between them. So again, in this case, the separation is 1.43, but because the top and the bottom one are 1/2 of what all the other resistors are, then that separation here is going to be 1/2 of the 1.43. Okay, so it's going to be 0.71 and maybe some change there. I didn't print out those values, but that's the way that these converters work. So what happens, this is the case for a 3-bit converter. All right, so if you wanted to go to, say, a 4-bit converter, okay. So a 4-bit converter, you would have 2 to the 4 bits, which gives you 16 possibilities, right? But one of those possibilities are simply all zeros. And so it'd go from all zeros to your last possibility of all ones, which is going to be 15. So you could have 15 non-zero values. So your resolution, the resolution then is going to be 10 volts, because in this case we're going from 0 to 10 volts. So our resolution is going to be 10 minus 0, the high limit minus the low limit, divided by the 15, which is your high value here, divided by your low value, right? And this is just the slope, really. But you're going to have 10 divided by 15, which is going to give you let me change the color here. So I would have my my volts per division. Okay, if this was a 4-bit now, my volts per division would be 10 divided by 15, which is going to be 0.667 volts per count. So every time we went up a count, every time we go up a count, we would be stepping. There would have to be a change of about 0.666 volts. It's actually right 666 all the way out, because this is basically the 1 divided by 3, right? Or excuse me, 2 divided by 3. It's basically 2/3. So it's going to be like 0.66666 forever in there. So I'm just rounding up just a hair. But the first value then we would be able to detect down here, we would be able to detect half of that, right? Which would be, so the very first voltage we would be able to detect would be 0.333, and again it technically goes on forever, volts. All right, so that would be for a 4-bit converter. And then the highest, what's the highest if we were doing a 4-bit converter? Okay, so for the 4-bit converter, the highest value that we could do would be 10 minus the 0.333, right? And so that would be 9 point 667. All right, and so that would be the maximum voltage that the 4-bit would be able to detect. And you can just go on, you know, you can do a 5-bit, 6-bit, 7-bit, you know, however large, you know, however many comparators that you want to build into the circuit, and you just build your resistive circuit there and feed those comparators, and you can make it more precise, right? So every time you add a bit, okay, so again over here we were on the other screen we had a 2-bit. So the 2-bit converter for 0 to 10 volts was giving us a 3.3 volt. And then a 3-bit means we have a resolution of 1.43 volts. And a 4-bit means we have a resolution of 0.667 volts, and so on. So that means that you can detect smaller changes. The more bits you have, it means the smaller change, you can detect smaller changes. So the more accurate it is, or the smaller the resolution means that you'll be able to detect smaller changes in the signal coming in.